G'day, my name is Paul Arden and I'm the CEO at migenius, and a little later you'll hear from Thomas Diedrichsen, a Senior Software Development Engineer at Amazon. So you've heard of software as a service, platform as a service, infrastructure as a service, but what is visuals as a service? We'll cover four main areas. First, a quick overview of why quality visuals are so important for any business which makes physical products. Then an overview of different techniques for creating visuals, followed by a solution that we developed for creating visuals as a service. Finally, we'll dive into some real-world use cases of customers who are already using this technology, including a presentation from Amazon. So why are visuals so important? Now, it might seem obvious to say, but every manufactured product needs visuals. Imagine purchasing products without visuals. Would you buy this jacket? It's from a reputable brand. They promise it'll be the right color when you get it. All the features, price, materials are there. Still not interested? Of course not. You want to see the product. Companies expend significant resources testing what visuals work best, and they repeatedly find that not all visuals are created equal. So how are visuals being created? Companies use many different techniques. Classical photography is certainly one, but we're not going to focus on that here, and instead we're going to focus on 3D rendering techniques. Pre-rendering is a simple approach where you take your materials, geometry, textures, lighting, and so on, and generate a static image that you upload to a server and then serve. There's no flexibility, everything is pre-generated in this case. Compositing is an approach where you take different fragments of a complete visual and merge them together to produce the final visual at the end. This is more flexible because you can change the individual options. Server-side rendering moves the rendering work to the server, so everything can be done dynamically. It allows you to keep the quality, but also generate things dynamically, which means no pre-computation. This can be great in cases where you have a very large number of combinations. If the quality is not really a big concern, then client-side rendering is also an option using technology like WebGL. Most machines now that can run web browsers can also run 3D content in some form or another, but often you'll need to use a lowest common denominator approach because you want to get the widest possible audience, and the capabilities of 3D hardware varies quite widely. Now, I've glossed over some details here due to time. However, these days, regardless of the technique you choose, you'll almost certainly be using some form of PBR or physically based rendering. There's many other talks available on that topic, and I definitely suggest you check them out. So which technique is best? As always, the answer is it depends. Let's dimension the question with a few key characteristics you'll need to think about. Quality, flexibility, speed, how easy it is to deliver, and how low the upfront effort is. For pre-rendering, you can have as high quality as you like because all the generation's happening in advance. You don't get any flexibility though because everything is set. Speed of delivery is going to be very fast because all you're doing is downloading images. And it's also very easy because you're just serving up images from a server or a content delivery network. However, there's a lot of upfront effort in computing those images. Using compositing, you can get very good quality, maybe a little bit lower than fully pre-rendered, and you get extra flexibility because you're even still generating pre-generated content, but in smaller fragments so you can change them more easily. Speed is also going to be reasonably good, but maybe a bit slower than pre-rendered because you have to actually do the work to composite the content in real time. Delivery is therefore also a little bit more resource intensive. Upfront effort is obviously going to be less than pre-rendered, but more than server-side rendering. On the server side, you can get full quality and flexibility because nothing's pre-generated, but you're going to lose some speed because of the fact that you're generating all this stuff on demand in real time. Ease of delivery is also reduced because you have to have server resources to generate these images, and that might be GPU servers and so on. But there's no upfront effort because you don't have to generate any content in advance. When using client-side, the quality takes a big hit, but flexibility is great because you can generate everything on the fly on the client side. Speed of delivery is also great, with WebGL being mostly real-time in most scenarios these days. Delivery is not quite as easy as things like images because the content is quite a bit larger, but it's definitely more straightforward. Obviously, you're going to be downloading bigger pieces of information. There's also very little or no upfront effort because you don't have to do any pre-computation unless you're doing baking and things like this. So while there isn't one easy answer to which technique you should use, there are a few things you should consider when making your choice. The first question we always ask is how many visuals will you actually need? And this comes down to combinatorics. If you don't remember the subject of combinatorics from school, this was all that 5 choose 3 stuff. Basically, how many combinations and permutations are there of your product? We refer to this as the size of the configuration space. Dimensioning this is critical to choosing the right solution. If the total number of combinations is relatively small, say 10,000 or so, you're always better off just brute force rendering everything. That's going to be the easiest and highest quality option that you can have. Remember though that things that are not product options but affect the visual should also be considered part of the configuration space. So for example, the view orientation, if the user can navigate around. Think about whether you really need completely free rotation in 3D or whether discrete steps, in a turntable type solution might be adequate. Anything that has arbitrary freedom, for example, free navigation or spinning around the model, or user uploading content such as photos or floor plans, immediately gives infinite combinations. So these configuration spaces explode very quickly. In these cases, pre-rendering, compositing, or even server-side rendering with caching is out of the question. You really need to have something fully dynamic. So you're going to have to go with server-side or client-side rendering for that situation. Actually, it's not entirely true. There's a couple of use cases where we have some little tricks we can do with compositing to help make that work. Hopefully some of these points make it clear that you must understand the configuration space when building applications in this area. Don't skip this upfront investigation. It's important, and it can really bite you later on if you don't think about it upfront. There are many more things to consider when choosing your technique, particularly for customizable products. We don't have the time to cover them all here. However, back in 2014, we published an article which covers a lot of ground. While some of the technology has improved since then, much of the ideas are still relevant today, so I'd encourage you to check it out here. Over the years, we've had to use all the different techniques we've just covered to allow customers to create visuals. Our reality server product is an approach to combine all those into a single solution. Before jumping into some use cases, I want to talk about how we decided to approach solving this visuals as a service problem with Reality Server. Cloud first was a clear requirement from the start for us, so we decided to make the solution a web service. To use it, you just need to be able to make HTTP requests, that's it. More specifically, in our case, we chose JSON RPC as the protocol for our service. We're sometimes asked why not a RESTful API. However, with 3D data, you can't really get around having to have a state. 3D data is big, and recreating the state for each request is not really practical. So we went with a remote procedure call approach. JSON RPC is lightweight and easy to use. It's just the commands and parameters. You can see an example of that on the slide at the moment. You can put multiple commands into an array and send sequences to the server. This little sequence loads up a scene and renders an image. And you can also simply call it with something like curl or postman or these sorts of things. You can see an example calling it with curl there below. For rendering, our initial focus was on high quality imagery, whether pre-generated or live. So we decided to use the iRay rendering engine for this purpose. iRay is physically accurate. It's a bidirectional path tracer and is heavily GPU accelerated. iRay also offers a faster, less accurate mode called iRay Interactive, which in many cases can be used for quicker rendering. It's a progressive renderer, so the results start out with some noise and refine to a completed image. Using the newer AI denoising techniques, you can also speed that up even more. Rendering with Reality Server can be interactive and streamed directly to the browser. We use WebSockets for that. Or you can use a more batch-like approach. The streaming is currently using a JPEG image stream, but we are also working on H.264 video with low latency for solving that problem as well. We chose to lean on others for the queuing solutions for Reality Server. So if you want to do queuing, we have an Amazon SQS-based queuing system for that. That lets you queue up any task. Tasks are just JSON RPC commands, and then execute them on your servers. If queues get too long, you can just add up new servers and they pick up the work. Most cloud providers have an automatic way to handle this sort of thing. So AWS has auto scaling, for example. AWS queuing is what we support now, but we're also looking at Azure and Google queues in the future. Without programmability, all this would be just a glorified render farm. What we really needed was a way to code behaviors to turn the 3D data into visuals. Imagine you have a web page which creates floor plans and outputs data on the wall locations, window positions, and furniture locations. To generate visuals, you would need to create the wall geometry dynamically, cut holes, place the windows, place the furniture around the space, and then generate the imagery. A pre-generated approach or a predefined approach won't cut it here. We chose to use JavaScript as the main language for coding these behaviors. Specifically, we used the Chrome V8 JavaScript engine, mainly due to performance. Using this approach, I've personally coded applications using our server-side JavaScript in a few hours to handle use cases like the one I just described. For hardcore developers, you can still get into the weeds with the C++ API if you want, but really, we're not really finding much need to do that anymore. On the slide at the moment, you can see some example of some simple JavaScript that's loading a scene, setting some camera options, and so on. You might be detecting a bit of a theme here in that what we're trying to do with Reality Server is target all those different techniques I mentioned before. So what about compositing? So compositing could actually always be used with Iray for a long time because it can generate outputs with things like masks, depth maps, alpha channels, and so on. Those were the more traditional compositing approaches, and you can still use those in many use cases, and some of our customers do. However, when it is just materials and lighting changing, there can be better ways to do this. Iray includes a feature called light path expressions. Arnold and RenderMan also have this, and you can use that to do compositing. I'll cover that in a little bit more detail later. For addressing the client side of the techniques we mentioned, we've also moved recently to support WebGL in a big way. If you're not familiar with GLTF and WebGL, GLTF specifically is a transmission format for 3D content. It's developed by the Kronos Group, and it supports all the basic features needed, including PBR materials. It's now getting widespread adoption, and in Reality Server, we decided to allow both ingestion and output of GLTF. This makes matching client-side and server-side rendering much simpler. It also leads to hybrid use cases being very practical. Taken together, this functionality allows you to build a visuals as a service solution where you just need to bring along your business logic and code that in. All the hard parts are taken care of for you. I've picked 3 different areas of our implementation to go into in a little bit more detail. The use of Iray for rendering brings with it the adoption of MDL, the material definition language. Appearance is something that's often overlooked. MDL offers a way to represent virtually any material appearance in a standard format. It describes what to render, not how to render it, and this is important for efficient execution on the GPU and ensuring physical accuracy. It's now open source and you can use it in your applications, and it has an interesting feature called distillation. This allows you to take a material and simplify it into a target model that you can use in your application that doesn't support MDL. There's also a vMaterials library, V for verified, which is provided by NVIDIA with over 2,000 materials that you can use in your applications. Being renderer independent is a great advantage with MDL because it allows you to build large data repositories where you don't have lock into a particular rendering technology or other piece of tooling. As you'll see in a minute, it's also not just for rendering. We can use it for some other use cases. Light path expressions are a way to address some of the downsides of compositing for generating visuals. Think of light path expressions like regex for light paths. These allow you to separate the contribution from different light paths into different images that you can then combine later. Here we see some example expressions where we're separating the laces and stripes for this particular shoe in their direct and indirect components. What we're getting here is contributions, not passes. So these are actually the contributions that those light paths will make to the final image. In this case, you're seeing the direct and indirect contributions, for example, of these different pieces. There's also a residual computed here, which is the expression that captures everything that's not captured by everything else, and that needs to be added together to get the final image. The final image then is just adding the pixels together, literally adding. There's no masking, there's no alpha channels or anything like this. It's just A plus B plus C. Now, of course, if we just added the images together and got the same result, that really isn't all that useful. So what we can do is tint the different contributions to get different results. So we can now create any number of combinations of colors and even user-generated colors without having to re-render. Notice in this example, there's no edge artifacts even around the stitching and even the stitching in the out of focus areas. Another trick we can do is to apply arbitrary texturing by uploading textures and then using the UV channel that we've computed into a separate image to warp the image as it's applied to the tint. GLTF has become increasingly important for us in deploying visuals as a service. It's a standard format developed by the Kronos Group and is in widespread use, and many of our customers today are bringing assets in this format already. It has a nice PBR material model built in, which lets you make decent looking materials even without the use of MDL. This is really helpful for matching client and server-side rendering, so that they can pass the squint test, as we call it, between the different rendering engines. You can do this automatically now with distillation using the MDL material distillation system. Another initiative I mentioned is the 3D Commerce initiative, also by the Kronos Group, and this is definitely something you should take a look at, as I think it will evolve into something useful for defining 3D formats in the future. Bringing all this together, we see visuals as a service being a unifying approach for all types of visual output. We're focused on imagery and web-based 3D content, but there's also AR and VR that are becoming increasingly important. While still evolving, businesses are already using visuals as a service approaches to solve real problems today. Let's look at how some different businesses are using visuals as a service right now. Timex are well known for their quality watches and sell through many retailers. Working together with Technicon and Tacton, migenius has created a visuals as a service solution based on Reality Server to create high-quality visuals from configured watches. Internally, Timex design teams are able to create and view products and validate their appearance. These teams are using the full server-side rendering solution with dynamic rendering. When ready to sell, the same content and systems are being used to produce thousands of required visuals for online retailers. This is done with pre-rendering using Reality Server and queuing. Despite requiring many different formats for each retail, the process is able to be fully automated. It's now reached a point at which the visuals generated from 3D content are replacing traditional photography, with significant savings in both time and marketing budgets. Two of the techniques we discussed here are being used, selected to match a particular use case. Interactive server-side rendering for the B2B internal rendering use case, and pre-rendered for the B2C side of things. This shows why it's important to think about the techniques carefully in advance while planning your product. Tetra Pak are a world leader in processing and packaging solutions for food and beverages. While they might not be a household name, you'll find a Tetra Pak package in almost every household. Peek behind the flap of your milk carton and you'll likely find the Tetra Pak logo. Tetra Pak customers need to see what their package designs will look like on the chosen Tetra Pak product. The Tetra Pak Package Visualizer is a web-based application built on the Reality Server platform for just this purpose. Users can select their package and then upload their design files. Photorealistic results are rendered interactively, allowing the user to navigate around the package and inspect any part they like from any angle. For package designs, it's particularly important to see a realistic 3D representation of the end result. Usually designs are created in 2D illustration software, and it can be difficult to understand how they'll work on the real packages. Once the designs are finalized in the system, you can produce high-resolution still images for approvals or marketing purposes. These images help ensure sign-off before proceeding to the next stage and aid in selection of appropriate packages. For food and beverage products, the final appearance often rests on the package design, making it critically important for marketing. Again, the two techniques used here, but for different reasons. In this case, there is user-generated content, the uploaded package designs, and arbitrary viewpoints, so we have to use server-side rendering for this approach because of the quality requirement. So the configuration space is essentially infinite. Quality must be photographic, and really server-side's our only option there. Pre-rendering is also used for the batch generation of the higher quality images of the end products. For our next use case and to finish our talk, I'll now hand over to Thomas from Amazon, who will talk about how they're using Visuals as a Service in their business.
Hello, my name is Thomas Didriksen. I'm a software engineer at Amazon, and I work on a variety of 3D related projects, including rendering and 3D asset creation. In this presentation, I will cover some of our current work on 3D driven customer experiences and discuss how the Reality Server product from migenius has provided us with a flexible foundation for automation of photorealistic rendering. As such, I will focus mostly on use cases that involve offline rendering, but to give a more complete overview of what we're doing with 3D at Amazon, I will discuss a real-time rendering use case as well. First, I will give a brief overview of our 3D processing architecture. After that, I will dive into 3 select customer-facing 3D-driven experiences, namely synthetic product photos, an interactive experience we call Showroom, and finally Amazon's mobile augmented reality experience. First, architecture. This is a high-level and somewhat simplified overview of our ingestion, rendering, and quality assurance pipelines. Starting on the left-hand side of the diagram, we receive high-fidelity 3D assets from a variety of sources. These assets flow into the ingestion pipeline and are ultimately stored in a cloud-based asset management system hosted in AWS. From there, we can create a variety of derived assets customized for specific use cases. Several of these use cases requires photorealistic rendering in order to enable compelling customer experiences. For this, we rely on Reality Server from migenius. Specifically, we've deployed Reality Server in an AWS EC2 elastic compute environment that allows us to seamlessly scale capacity as needed. Today, we are using EC2's P3 instances, which offers up to 8 NVIDIA V100 Tesla accelerators per instance. We found that this hardware configuration performs exceedingly well with Reality Server and iRay. For other use cases, we employ format transcoding and compression to make 3D assets more suitable for real-time rendering, for example in mobile user experiences. Note that all customer-facing assets are subject to a quality assurance process before they're released and made publicly available. Finally, we deploy the assets to the various customer experiences shown on the right-hand side of the slide, including synthetic product photos, the showroom experience, and finally the augmented reality experience, which relies on reduced fidelity 3D assets in order to achieve real-time performance. In the remainder of this presentation, I will talk about these 3 use cases, starting with synthetic product photos. Having high-quality 3D models and materials in combination with the rendering capabilities of Reality Server and iRay allows us to generate convincing synthetic photographs at scale. These are examples of rendered images that you can find on the Amazon website today. Notice how the rendered image on the right makes subtle use of depth of field to increase realism and accentuate certain product features. Reality Server provides full programmatic control of the scene, including the lighting setup and the camera configuration. When rendering thousands of products, this makes it easy to achieve a consistent and aesthetically pleasing look. This is important when multiple products are shown side by side on a search result page, something that is difficult to achieve with traditional photography. We also render frame sequences or animations like this 360-degree view that would have been difficult and expensive to capture in a photo studio due to the physical size of the product. We use Reality Server's scene manipulation functionality to dynamically position the camera so the product never rotates out of frame. Here we see another example with a garden bench. In this case, we rendered a more elaborate scene including the product alongside props like flower pots and plants in a realistic environment, all 100% synthetic. In these examples, we've taken that concept a step further and placed multiple products in the same scene, along with props to create realistic lifestyle photography, like this sunlit living room and bedroom. On the left, we see another example where we use larger scenes and props to bring the product to life and show it in the intended context. And yes, the hummingbirds are 3D models too. Again, a shot that would have been difficult and expensive to achieve with traditional photography. On the right-hand side, we see a comparison between an actual photograph and a render done with Reality Server. Capturing well-aligned, well-lit, and blemish-free close-ups of small electronic products can be time-consuming using traditional photography. With photorealistic rendering, we can generate consistent results faster. Next, let me introduce another customer experience that makes use of some different features in Reality Server and iRay. The experience is called Showroom, and is currently available via amazon.com/showroom. It allows users to interactively furnish a room and get a sense of how custom combinations of products appear in context. Here's an example of what the experience looks like. You see a furnished room, and you may select different elements in the room that you wish to change. For example, you may swap out the sofa, or the chair and coffee table, or perhaps the lamp, the wall art, and so on. You're free to combine different products to your personal preference to help guide your buying decision. With a large amount of products to choose between, the combinatorial explosion makes it infeasible to pre-render all possible variations. Instead, the individual products are rendered as separate layers and subsequently composited together interactively in real time. Let's take a look at the parts that goes into a showroom scene. The walls and ceilings are rendered separately. The floor layer is rendered in multiple color and material variations. Notice how reflections from the window and the ambient occlusion near the walls is rendered realistically. And finally, the individual pieces of furniture. Notice how the color cast and the shadows from the furniture is rendered onto shadow catchers, thereby generating shaded output with proper alpha transparency to produce more realistic results during the subsequent interactive compositing stage. Adding all the layers together and we get the final scene. For Showroom, we use Reality Server's material and scene manipulation functionality to configure and render the many individual layers. Automatic rule-based systems determine the render configuration by taking product category and the physical product size into account. The individual render jobs are subsequently scheduled in the render farm where we dynamically manipulate materials and position models so they appear in the intended locations. Finally, I will demonstrate the mobile augmented reality feature that is currently available in the Amazon mobile app for iOS and Android. The experience allows customers to visualize 3D objects like furniture using augmented reality. Customers are guided through a process that establishes a floor plane on which 3D assets may be placed. After that, the model may be inspected by physically moving the device around in your space. So to summarize, 3D-driven customer experiences are becoming increasingly common at Amazon. In this presentation, I've shown a few examples of this. For some product types, we see photorealistic rendering as a viable substitute for traditional photography. In some cases, even superior to traditional photography in terms of cost, consistency, and flexibility. We've chosen Reality Server from migenius as a key enabling component for our render automation. From an engineering perspective, Reality Server has been straightforward to integrate and deploy. We found it to be reliable, with feature-rich capabilities that has enabled us to meet our diverse rendering requirements. Thank you for your attention.